All right, guys, so now we're on to section 10.6, which is segments in circles. A couple different theorems here. This first one, not too bad. The other ones get really interesting. In fact, I'm not even going to give you the definition from the book because it's so wordy. I'm going to try to simplify it a little bit for you. But this one is not too bad. So this is a case where you just have chords that intersect each other. Okay, so last few days we've been looking at angle measurements and how we could calculate those based on arc measures. Today we're looking at the actual lengths of the segments themselves. Clearly the only way that we know how to do that right now is if we knew where the center was. We would know that these were radii. But with the intersection being anywhere else in the circle, we have just a chord, two chords that are cut up in different ways, okay? But they do actually follow a pattern. And that pattern is that if two chords intersect in a circle, okay, we'll do some intersecting segments outside of the circle next. But if the two segments intersect inside of the circle, okay, the products of the segment lengths of each chord are equal. So to demonstrate that with a little bit of color, okay, what that means is that if you take one of these chords, AB, okay, so the product of the segments of this chord, okay, so the chords of AB, the chord AB has segments AE and EB, okay, and then the segments in the second chord are from D to E and E to C. So that is going to be, okay, so this is equal to TE times EC. Okay, so essentially the product of the two pieces of each chord are equal to each other, right? So what does it look like here? So if I have this piece, we're going to have a couple things. These things are going to be equal to each other. So this chord ML is made up of MN and NL. So the product of MN and NL is equal to the product of the pieces of chord KJ, which are KN and NJ. All right, so the product of the pieces should be equal to each other. So that means that our x plus 2 times x plus 1 is equal to x times x plus 4. So this gives us the quadratic x squared plus 3x plus 2. This gives us the quadratic x squared plus 4x. And if we subtract x squared, those cancel. And we subtract 3x, it's going to give us x equals 2. So the two things that we want are ML. Okay, so if x is 2, then this piece is 4, and this piece is 3. So ML is 7. And if we look at the other piece, KJ, or JK, is made up of the small piece of x, which is 2, and this is 2 plus 4, so this part 6. So KJ is 8. And those are our two solutions there. Okay, so that's our first theorem. Chords that intersect in a circle, the product of their individual pieces are equal to each other, right? Now this one is where it starts to get difficult. If you want the actual definition, it is on page 682. All right. Actually, if I could, I'll just find it. I'll read it to you. So The definition of this says that if two secant segments share the same endpoint outside of the circle, then the product of the length of one secant segment and its external segment equals the product of the length of the other segment and its external segment. Okay? This definition uses a lot of vocabulary that is kind of new. Essentially, it's looking at this secant segment here, EB, and kind of separating it into this piece, which it's calling the external segment, and the whole piece, which is calling the secant segment. Okay? Now I have a much better way, a much better way of memorizing this. Like I don't really keep track of all this kind of craziness in my head. And so what I do to remember this, looking at the individual secant segments, is I say to myself that the distance, the length to the circle, so to the circle times the length through the circle is equal for both segments. Okay? So what do I mean by that? So that means if I look at this secant of EB, if you start from the external segment, okay, to the circle is EA, okay, to the circle is EA, and all the way through the circle is EB. Okay? And with the other secant, we have from E, the length to the circle, so to the circle is EC, and the length all the way through the circle is ED. Okay? So I just remember this, to the circle times through the circle. All right? So 2 times through. And so it's very similar. It's similar enough to the first one in that both of them we have E labeled as the intersection. So it's E to the edge, E to the edge, right? So you have E to the edge, E to the edge. And these are the same thing. E to the point, E to the point. All right, so it's similar in that respect, okay? So starting from the intersection point, you go to the circle, through the circle, all right? That's easy enough to lose track of. Unless you write that down. Okay, so I'm gonna write that down so I don't make a mistake here. Okay, so I'll start all the way from scratch. So I'm just gonna write to the circle times through the circle is equal to the product of the lengths to the circle and through the circle. Okay, so if I look at the top one here, TR. Okay, to the circle is TS. All the way through the circle is TR. Okay, to the circle is TU. All the way through the circle is TV. Okay, so if you write this down, you're already halfway there to not making a mistake. All right, so now to the circle is TS, which is 15. And then all the way through the circle, the thing you want to be careful of here is a lot of times people, maybe it won't happen here because the numbers are a little bigger, but this, I'll show you with the next one. It's very easy to make this mistake. The whole segment, you have to add these. So the whole segment TR is 3x plus 15. Okay. That might have not tripped you up, but if you look here, for TU is 20. Okay. And all the way through the circles, both of these combined. Very common mistake is people say 20x. They just put these two things together, but that's multiplication. So to the circle is TU, so that's 20. Through the circle is the sum, so that's x plus 20. Okay, super common mistake. Especially when you have just an x, you just tack the x onto the number, and you're actually doing multiplication there. All right. So if I multiply these things, this is 45x plus 225, and this becomes 20x plus 400. So if we subtract the 20x, that gives us 25x on this side. Subtract the 225, that gives us 175. And then divided by 25, we get x equals 7. Okay? So that is to the circle, through the circle. All right? So a few practice questions here. All right? Again, why don't you pause here, try these, okay? And then maybe I won't show all of them. I'll just give you the answers. All right? So the first one comes out not too bad. We get x equals 13. The next one is just the chords. So you're looking at the product of the pieces. This one's should be pretty straightforward. This one ends up being 8. This to the circle times through the circle, this ends up giving you a quadratic. So if we try this out, so this is to the circle here is 3. All the way through you have to add these, so that's x plus 5. And then to the circle here is x plus 1. And through the circle means you have to add these. So you have x plus x, which is 2x, negative 1 plus 1, which is 0. So this gives you 3x plus 15. And this is 2x squared plus 2x. So when you set this equal to 0, you get 2x squared minus x minus 15 equals 0. And this factors, you can just factor by grouping. I'm not going to show all the factor by grouping steps, but this ends up being x minus 3 times 2x plus 5. So this gives you a solution of x equals 3. The other solution here of negative 5 halves, negative 2.5, is extraneous because it would give you negative segment lengths. So that one is no good. Okay. Now the last theorem here, this is, I like to consider this not a new theorem. Okay. So the one we talked about had a secant, 2 secant segments. So this is a secant segment here. Okay, so it hits through the circle twice. This one right here, though, if I were to label this, this is a tangent segment. Okay, so it runs tangent to the circle, so it only hits the circle once. All right, it lies tangent to the circle. So I just want to show you where we can almost quasi-derive this. So if I pretend that it's the same, so pretend I don't know this is a tangent. Pretend we just think these are 2 secant segments, okay? So I'm going to put this in quotes here. So we have to the circle through the circle is equal to, as we know, to the circle times through the circle. Okay, so pretend it's the same thing as the previous theorem, because it is. Okay, so pretend it's the same thing. In this case, to the circle, EA, is actually the same thing as going all the way, quote unquote, through the circle, because it just lays tangent. It is not secant. So it is just EA twice. And now here, to the circle is EC. And through the circle is ED. So this thing's the same. So this is EA squared is equal to EC times ED. Okay? And so that is really the kind of shortcut for this particular piece, okay? Which is that the tangent segment squared is equal to the product of to the circle times through the circle. Okay? So I like to not even think about this as a new one. I just think to the circle, through the circle for both of them. But in this case, the to the circle and the through the circle is the same thing. Okay, so you need to put in the same thing twice. That's why it ends up being squared. So quickly an example here. The tangent piece squared is equal to the circle times through the circle. So we have RS squared. To the circle is RQ. All the way through is from R to P. Okay. QP is the part that we're trying to find. So that's going to be our variable here, x. So RS is 36. So we have 36 squared. To the circle is 24. And that means all the way through is going to be x plus 24. So 36 squared is 1296. Okay. And then this becomes 24x plus 24 squared is 576. We can subtract the 576, and we get 24x equals 720. And then dividing, we get x equals 30. And so x is just what QP is, so QP equals 30. Okay? So again, you just want to use that idea. To the circle times through the circle. All right? So I'll pause here, try these. I'm going to set most of them up and just give you the answer. There's, I think, maybe one or two that I actually want to do here, though. All right. So first one here, we have the tangent. So the tangent segment squared is equal to the circle times through the circle. This ends up giving you x equals 2. If you forget, just pause and try these. I'm going to run through these very, very fast. Okay. Here, tangent squared is equal to the circle times through the circle. This ends up giving you 24/5 or 4.8. This one, tangent squared is equal to the circle times through the circle. Okay. This gives you a factorable quadratic where a equals 1, so it's pretty easy to factor. So you get x equals 8, which is the only correct answer. The other extraneous solution is that x equals negative 18. So that one does not work. Number 7, again, we have tangent segment squared, okay, is equal to the circle times through the circle. All right. This gives us a very ugly quadratic. So this one I'll show you. So this becomes x squared plus 14x. If you set this equal to 0 and try to factor it, it's actually not factorable. So it's not a nice answer. So you could use the quadratic formula. But since I already have it here, all right, and the lead coefficient is 1, and the middle number is even, I'm going to complete the square. So completing the square, I do that by taking half of the b value and then squaring it. So half of this is 7. 7 squared is 49. So I'm going to add 49 to both sides. Okay. And so that's going to give me 274. And that makes this factorable as x plus 7 squared. So it completes the square into the perfect square of x plus 7 squared. So when I take the square root, I get plus or minus the square root of 274 is equal to x plus 7. So I can solve this by subtracting 7. So that gives me negative 7 plus or minus the square root of 274. Negative 7 minus this is going to be a negative number. So that obviously can't be correct. So this is going to be 7 plus the square root of 274. That may simplify. I don't think it does, though. But maybe it does. Okay. Correct me if I'm wrong. My gut tells me that's a no. So that's number 7. Number 8 is just the product of the pieces of the chord. So this one's pretty easy. You just get x equals 8. And then the last one here, we have another to the circle, through the circle. So to the circle is 18. Through the circle is 18 plus 22. To the circle is x. Through the circle is x plus 29. So the numbers are a little big. It does end up giving you a quadratic. The quadratic is factorable. It's not super easy to factor. It ends up being x plus 45 and x minus 16. So the numbers are a little big. So again, that gives you the solution of 16. The negative 45 is extraneous. Okay. Good luck. Take care.